Card. All right, so we can do phase change. All right. Now let's look at water. Right. So this is the structure of water. Pay keen attention to your temperature. Right. Remember we spoke about Kelvin, and anybody remember Kelvin? The relationship to Kelvin and um Celsius, degree Celsius.
So
All
you
right.
said they were the same.
Okay.
They were the same.
I didn't hear that. I didn't hear that.
Oh, I thought you said they were the same, sir.
Yeah. So 1 degree Celsius is the same size as one Kelvin, right? But the Kelvin scale, right, really begins at it starts at negative. So 0 degrees is equal to 273 Kelvin. All right, so 0 degrees. So if we want to go to 0 degrees, we'd have to go to 273 Kelvin. Now, this is essentially water in a solid form. We can see that the particles are close together, therefore they have some form of structure like water. They're not randomly displaced. If we apply heat, we see that there's a change, right? We see that there's a change in the behavior of the molecules. We see that they become a lot more let me bring it down to let me bring it to how much is this? Yeah, so this is minus 3 degrees Celsius, just below the freezing point. We say the particles are still close together, right? Still close together, and they are breaking apart slowly, right? And they're getting more energy. So therefore they're much more active and essentially hotter, right? As we discussed. The more kinetic energy that the molecules have, you'll find out that they will have more heat. So the more energy you apply, you find out they have more heat. Now, if we add more heat to 273 Kelvin, which is at 0 degrees, right? You you will realize that the particles will start to move a little more apart, and some particles will start to break away, just as this one. So this means that they are becoming liquid. They're going from a solid to a liquid form. We see that the particles are more stretched out. There's no more structure. Are we seeing that? The particles
Yes,
are,
sir.
yeah. So they're looking more like a liquid. All right. Now, if we apply heat, we apply heat, say up to room temperature, approximately. Let's say let's put that 25. 10 more. All right. We see that the particles are getting more energy, right? Therefore, they are moving a lot more. They are moving a lot faster, and they have more kinetic energy. Therefore, they have more heat. That's how I wanted to describe the behavior of molecules. Go back to the kinetic energy theory that we spoke about last week. Particles, all the kinetic energy theory, as we spoke about last week, all particles have some form of kinetic energy. Therefore, they all have random motion. All of them have random motion. So therefore, um, if you apply heat, the particles will get more kinetic energy. Therefore, the temperature of that system will rise. All right. And if we apply more heat, let's say up to 100.
There's pressure affect nothing.
All right, we're not troubling pressure for now, right? But if you change the pressure, we can look on that quickly. Yeah, but we'll save that for gas laws. We're not going too deep in that as it. 29. change this to that I understand. So we change it to 100 and we observe the behavior of the molecules now, right? We're seeing that they're slowly breaking away from the structure, right? And what is happening here?
Particles are moving
It a bounce. So you change state.
All right, so there's a change of state from
Liquid to gas.
exactly. So there's a change of state from liquid to gas. Particles are beginning to break away from the structure, right? So there's no more structure like was that we saw in the ice, right? At 100 degrees, the particles are slowly going away, slowly going away. If we apply more pressure, let's kind of quickly, right? Or wait, let's it's decreasing the volume. Let's apply more pressure. Right? We see the behavior of the particles now, right? So there's more pressure in the system. We see that the particles are moving a lot more vigorous, right? And as a result, they are applying pressure to the container. So every time they collide with the container, there is some form of pressure being added to the container. So we see that the pressure is constantly increasing. Yeah?
So that can cause condensation now in a pot.
Well, it won't cause condensation, right? It depends on it depends on the temperature difference, right? If this is hot inside and outside is really cold, then you would see some form of condensation, right? You see some form of condensation, right? But then because no heat energy is applied, right? And if this system is hot as 163 and outside is cold, you see for some form of condensation. Just as if you saw you have a cold bottle of water and you are ice water and you leave it in a hot environment, you see condensation building up. It's just the same. Let me see if I can find the other one. Right. There was one I had. I believe it's this one. Let's look on this quickly. Then I get back to all this. All right. So we place our water here. We place our thermometer inside. Right. And if we let's make it below 0. All right. If we add water, if we add heat now, see there's a temperature change. I'm looking for. All right, there's no readings here. This is not what I want. All right. This is for another experiment. All right. So the last one is good. We can work with that last one. So let's continue. All right. So we spoke about the four main changes of phase. Just a while ago, we looked at melting and boiling and what really happens to the molecules, right? But in real time, you will find out that the molecules will not change their the temperature. The temperature will remain at 100 until all our liquid is boiled. And you can test it, right? If you have a thermometer at home and you boil the liquid, right, you will find out that the temperature will not change. Let's move on. So there are two types of latent heat, right? We spoke about latent heat of fusion and latent heat of vaporization. Right now we say that latent heat of fusion is the heat required to change a solid to a liquid. So essentially melting occurs here, and latent heat of vaporization is used to change a liquid to a gas, and vice versa. So the same heat that is required to change from a liquid to a solid is the same heat that is um, given off by the liquid to go from a liquid to a solid. See if you understand what I'm saying. We try and explain this yesterday with this cup here. We apply heat to this cup of water, right? And we saw that there was a change of phase to gas. Now, if we have a cold system now, if we have a cold system, right, you would find out that heat energy will be released, basically pulled from our container. Therefore, that heat energy is heat latent heat of vaporization. So that will be pulled from the system to the environment, which would change it from a gas back to a liquid again. So let me know if you're following me, right? Are we good so far?
Yes, sir. No, that's
All right. Anyone not following me, please stop me. Let me know what is happening.
Sure, you can go over this.
Go over. Yes.
This particular slide, this one,
No, side from you.
I'm not hearing. This particular slide,
Not seeing any slide on the screen at the moment, sir.
I'm not hearing.
One second.
All right. So I am thinking, send a message in the chat, right? Type it in the chat because I'm not hearing.
Sorry, you hear me now?
Yeah, you were saying no. This slide here.
Yeah, tell us I'm never see no slide, but may I see it now?
Okay. Right.
I
So
have any piece of headphone.
all right. So you have
You know,
two
go.
types: a latent heat, right? And we said latent heat of vaporization and latent heat of fusion, right? The latent heat of fusion is the heat that is required to go from a solid to a liquid, right? And essentially the same thing is it goes this way, a solid to a liquid, and it also goes from a liquid to a solid, right? It's the same heat. And the latent heat of vaporization is used to change from a liquid to a gas and from a gas to a liquid, right? So the same heat. And when the latent heat is the amount of energy that is pulled, right, from the system or to the system, right, in order for a phase change to occur. So you realize when you're boiling water, the water will remain at 100 degrees. No matter how much you turn up the fire, it will remain at 100 degrees until all the water is released. Unless, of course, you have a pressure cooker, right, that will apply pressure to the system, and therefore the gas will not be allowed to leave. But if you have a regular pot of water and you check the temperature of that water, it will remain at 100 until all the the water is boiled or turned into gas. All right. So
Alright, sir.
okay, good. All right. So latent heat is gained during melting, right? This is for water, I believe. I So latent heat is gained during melting. Of course, when you're going from a solid to a liquid, as we saw in the experiment a while ago, we had to apply some form of heat, right? And latent heat is released during freezing by the system. So it's released by the system during freezing, right? And latent heat during vaporization or boiling, what is happening to the latent heat? Is it absorbed or released? So going from a liquid to a gas, do we apply heat or we take away heat?
take
Apply,
away,
sir.
sir.
Exactly. Exactly. So we
Oh,
apply
how?
heat.
because
You said, well, hold on. You said from a liquid to a
gas apply.
Right? Remember the experiment where a while ago we applied fire
oh yeah.
to the liquid looking set of the materials were in a liquid form, so they filled out the entire container, right? If you look at the solid, let me draw that quickly. If you look at the solid, it looks something like this, right? It wasn't perfect. The particles were inside of it, and they were always moving. Very important. Then in a liquid state, the particles look something more like this, right? And then for the final one, the particles would spread out from the liquid state, right? So they would spread out from that central block, all right? So heat is gained. When we apply heat, we get a liquid, and when we apply heat again, we get a gas, all right? And latent heat is released during condensation. So when we're going from a gas to a liquid, it's the same process, right? Um, is the same amount of heat, but different process by pulling heat from the system. All right, so whenever we pull heat from the system, you find condensation. All right. All right, so three common characteristics in the process of phase change. So a substance undergoes phase change at a particular temperature, right? Very important, this temperature is fixed. Fixed temperature, it doesn't changes. Heat energy is transferred during change of phase. So there's a transfer of heat energy, but there's no temperature change. Let me say that again. There's a transfer of heat energy to the system, but there's no temperature change until all the material has been changed. So until all the solid becomes a liquid, right? Or until all liquid become a gas. So during change of phase, the temperature remains constant even though there is transfer of heat as we just discussed, and the amount of heat required to change the phase of a substance depends on the mass and the type of the material. So of course, if you have water, right, and say you add alcohol, right, it would take a lot less amount of heat energy to change liquid alcohol to gas, right? Rather than water. Water would take a lot more heat energy to go from a liquid to a gas. And I know you have done this experiment and you haven't even realized that if you leave your alcohol out, right, and you don't cover your alcohol, what is going to happen?
I go on.
Exactly. So it's going to evaporate on you, and you're going to have to buy new alcohol. Or if you place alcohol on your hands you're going into a store and there's a sanitize, and you place alcohol in your hands, right?
As a
Good.
walk off a dry.
Exactly.
So it
And
is, sir. You tell me say alcohol itself, if in a cover, it not gonna be useful.
And then now gonna be used to get evaporate after a while.
So it smell like it not gonna be smell alcohol.
the aroma of alcohol will be there, right? But
Oh,
it
okay.
won't be useful to you. It will be useful, but not to you. You won't be able to use it the way that you want it, right?
Oh, okay.
And of course, if you have a small mass of water, right? If you have a small mass here and you have a larger mass, which one will require more heat energy to change a phase?
The larger one.
Exactly. So the larger one
Lord.
would have to have a larger amount of heat energy rather than this here. This would take a small amount of heat energy to change the phase. All right, so I want you to help me. No, we just discussed this. So there's a diagram. You're required to be able to explain what is happening on this diagram. Very important diagram, right? So let's start at the gas. This is in the gaseous form, and we see 100 degrees, right? And essentially is boiling water. When it's going back, we see that there's a change back into the liquid form, right? And then at 0 degrees, what is happening here?
Diyan maka-ice water.
Solid sir.
Diyan
Exactly.
maka-ice.
Exactly. And we see that even though we're adding heat, right? This is heat being added, right? It's getting hotter, but as it reaches, there's no change of phase until all, right? Until all of the gas, let's click on it again, until all the gas is changed to a liquid. Then you see this liquid begins to form, right? And then when it reaches down here, it gets colder, and then you see the solid begins to form.
Sir. Yes,
All right. So are we clear on this diagram?
yes sir.
Yes, sir.
All right.
Yes, sir.
Anyone not clear so far? Let me see. Anyone not clear? Please let me know. All right. Remember, you can interrupt me. I want to ensure that everyone is on par. All right. So note that at 100 degrees, both water and steam exist together, right? Let me check something here quickly. So essentially at 100 degrees, you'll find both water and steam, right? It's very funny and it's very hard to believe, but if you look at it while boiling, you have um steam coming out of the pot, right? You see that steam coming out of the pot. That's how you know when to put in a dumpling, right? When you see the steam start coming out. So both water and steam is in the system, and the temperature cannot rise until all the water is run away. If so, I'm saying this over and over again, just to make sure, right? Just make sure that we get this idea. So in practice, in an open pan, the steam cannot exceed 100 degrees as it gets its heat from the water, which cannot exceed 100 degrees. So at 0 degrees, both ice and melted water exists. All right, so ice and melted water exists at 0 degrees. So we can now talk about enthalpy. And this is the term used for the amount of heat energy supplied to a substance when it is changing state. All right, so some of this energy will go into raising the temperature, but if the substance expands, it will also do some work on the surroundings by squashing them. All right, so we're gonna focus mostly on the fact that it's the amount of heat energy supplied when changing state. All right. We are going to omit the fact, for this experiment, we'll omit this fact that it goes into raising the temperature of the system or the environment, because we are assuming that there's no heat energy loss because we are using an insulator. All right. So when I'm presenting a notes on Google Classroom, I will omit this for now, right? This is true, but for experiment purposes, right, we are going to assume that no heat energy is lost to the environment. So the word enthalpy can therefore be swapped into equations used later or instead of the term latent heat, right? The amount of heat energy supplied to a substance when changing its state. So enthalpy, latent heat. The most common one, latent heat. All right, so you will find most questions in CSEC on latent heat, but I introduce you to enthalpy just in case, right? Just in case it's a question with enthalpy. I don't want it to say, sir, we didn't go through this. All right, so enthalpy and latent heat is the same thing. So the specific latent heat, right? Remember specific heat capacity and heat capacity. What was the difference?
Mass sir. Mass.
Right. So mass. Could you help me with a definition, right? If you remember,
For what sir?
for heat capacity.
The amount of energy required to raise the temperature by Kelvin.
All right, and remember specific heat capacity.
Um
It's the same thing, but you just add on the mass, right?
mass. Yeah, mass.
right? So the amount of energy required to raise 1 kilogram of a substance by 1 Kelvin, right? And latent heat was the amount of energy required to change the phase of a substance by 1 Kelvin. But now we're going to get more specific. All right. So the specific latent heat of a substance is the amount of heat required to change the phase of 1 kilogram, 1 kilogram of a substance at a constant temperature, right? See this coming up back again, constant temperature. So the amount of heat energy required, right, while the material is at a constant temperature to change the phase to change the phase of 1 kilogram of that particular substance. All right, so it brings us down to our formula: specific latent heat. L, L is specific latent heat is equal to Q over M. And what we say Q is again?
Heat, sir.
All right, so Q is our heat, and where M is, of course, the mass of the substance in kilogram, right? So the SI unit for specific latent heat should be joules per Kelvin. We know that the heat, so let's do this, equal L equal Q over M. And what is our unit for Q? Energy.
Sir.
Exactly. So joules is a unit for energy, and the unit for mass should be kilogram. So that would give us joules per kilogram. All right, simple stuff, right? So we'll pause and then we come back. I will pause here and then we come back for the second session. Before we go to the next part, I don't want the thing to cut off on us. So hurry up and join. All right, and this is I will. We should be able to end class early today, so it depends on how early you join back. All right.